Okay, now we are gonna go a little bit more into depth for the MMF loss and inductance. Now we are gonna have the convention that if we are going from dot to cross, we are gonna consider the MMF negative, and if we are going from cross to dot, we are gonna consider that is positive. So this is in terms of angle. So let's say that this is pi by 2. So from pi by 2 to minus pi by 2, all of this the MMF is gonna be negative. So whatever we have here, we're gonna consider the MMF in this air gap, we're gonna consider negative, and from here to here, we are gonna consider positive. Okay, so now before we figure out how to calculate reluctance, but now we don't have a square. Before we have like a core, and we calculated the reluctance for the core, but now we have a different geometry. So let's see how that plays out. So we are gonna call this air gap G. So we know that the reluctance is the distance that the flux travels over the permeability of air times the cross-sectional area. And now the cross-sectional area here, remember this here we see 2D, but this is actually a 3D because it's a core and we have a rotor here. So our area is going to be pi r times L, where L is the length of the conductor. Okay, so in previous videos we saw that when the MMF in this air gap is equals to Ni over 2. So we are going to have Ni over T minus Ni over 2. And again, we have from cross to dot, we're going to say that is negative. And from the rest, we're going to say that is positive. So when we were to cross to dot, dot to cross, negative, cross to dot, positive. Okay? Also, we are going to say that we have a radius. This radio here is from here to here, to the limit path. Okay? Have a radius here. Okay, so how we calculated inductance based on this before was just that we have the flux, we have the MMF, and we divide it by the reluctance. Then we take it, the flux linkage that was n times the flux, and we said that our inductance was our flux linkage times I. So if we put our new values, we are gonna get that first our flux is gonna be Ni over 2 times 1 over this reluctance. And if we have 1 over this, we are gonna have mu naught times the cross-sectional area over G. And therefore, our inductance, we calculated that it was n squared mu naught RL over G, this is over 2 times pi. So this is a way to calculate the first way that we learned to calculate our inductance. Now, another way to calculate it is to, instead of consider the whole length of the conductor, or the whole angle phi, we are gonna consider it just a small one, a small angle phi here. Now, phi here is the angle, this angle here. we have multiplying here the radius uh, is not the flux. That's important to keep in mind. So we are gonna have that our reluctance now is gonna be G over our permeability over the of air, yes, times the radius times the length of the conductor times d5. Okay, so when we calculate our flux, we are gonna have that. Well, now we are gonna have a small piece of flux. So we are gonna integrate. Well, let me show you first. We are gonna have a small piece of flux. It's gonna be equals to Ni over 2 times what we figured out here, d5 over G. So this is gonna be our flux now. We have the reluctance by the MMF. And now to get our total flux, we just need to integrate this total flux. And where we integrate from wherever we have the dot to our cross. So in this case, we have from pi over 2 to minus 2 pi. So pi over 2 to minus 2 pi. So we're gonna get that our total flux is gonna be equals to here everything is a constant. Instead, the only thing that is changing is our angle. So we're gonna have Ni over 2 mu naught RL over G, the integral of, well, when we integrate the 5, we are just gonna get pi over 2 minus pi over 2, so plus pi over 2. And this is gonna give us our flux is Ni over 2 mu naught RL G times pi. And it's the same that we got here in our first case. So our inductance is gonna be the same. But now we are gonna see what happens if we have two inductances, two separate coils. So I'm gonna call this one A, I'm gonna call this one B. So we want to find mutual inductance of B with respect of A. So the inductance in B when we have a current in A. Let's say that so first we need the MMF in A. So we know that MMF is equals to Ni over 2. So we are gonna have Ni over 2 minus Ni over 2. Again, we follow our convention. So here we have our dot that is gonna be our A and A dash for our cross. So from dot to cross is negative, and from the rest we're gonna say that is positive. From cross to dot, we're gonna say that is positive. Now that we have the MMF in A, we can see how we can integrate with respect of the coil. Well, this is B and this is B dash. So we are going to integrate from B to B dash. Okay, so our flux in B with respect to our current in A. So we need to see from where to where we are gonna integrate. So here we have pi over 2. Over here we have this is 180 plus 30 degrees. So this is 210. And if we convert that into radians, we have that this is uh, 7/6 pi. Okay, okay, let's do it like this. We are gonna go from pi over 2 here to this one that is pi over 6. Okay, pi over 6. So we are gonna have in our MMF times our overall reluctance. That is what we just figured out here. G5. Remember, this is not flux, this is the angle plus. And now, okay, and now we are gonna go from here, 7 pi over 3 to 2 pi over 2, I'm sorry. Now, if we consider the MMF, let me just, from A, from A dot to B cross will be around here. The MMF is positive, so from this side is positive. But if we consider the MMF from B dot to A dot, so we have here B dot, and this is gonna go like this. So from B dot to A dot, that is gonna repeat around here. It is positive. It is okay. A second. B dot to A dot. Okay, see the mistake here. B dot is around here. Yes. So if we go from A dot to B dot, the MMF is negative, so this is negative. And the MMF is Ni over 2. And it is Ni because it's the self-inductance with respect to A. I mean, with respect to the current in A, the mutual inductance. Now we have our rest of the term, D5. Okay, so now we can integrate. So our flux is gonna be equals to Ni over 2. All of this just repeats because it's constant. And for this side, we're gonna have pi over 2 minus pi over 6. And this is minus Ni over 2 mu naught RL over G. And in this side, we have pi over 3 minus pi over 2. Okay, so we keep going. So now we can factor out our constant terms, and we are gonna have this subtraction minus this one, so this is gonna be pi over 3 minus 2 pi over 3, and this is just gonna give us that our flux BA is gonna be minus NA over 2. It's gonna be our what we have here. Minus NA over 2 times pi over 3. and therefore our self-inductance, our mutual inductance BA is going to be minus n squared mu naught RL over 2G pi over 3. Okay. Okay, now let's see an example with 3 coils. And we are gonna have here all AC. So we have again that we have again, because we are gonna do it with respect of the current in C, we're gonna have here in IC over 2, and here we are gonna have minus in IC over 2. So over here we're gonna have pi over 2, that is where our dot in A is. This is A, this is AB, A dash, this is B, and this is B dash, yes, this is C, and this is C dash. This is an example with three phases. Okay, now over here we are gonna have our cross for C. This is gonna be pi 5 pi over 6. Over here we have our 3 pi over 2, that is where we have our cross for A. So this is our B dash. And over here we are gonna have our dot for B. This is gonna be 11 pi over 6. Okay. Each coil is just separated by 120 degrees, so that's what we can figure out the angles. So again, we are doing it with respect of the currency. So we're doing it with this MMF. So when we have from dot to cross, we say that is negative. So I was writing B when I meant C. C. So, okay. So this is our C dash. Okay. Now, from cross, if we go from cross to dot, this is our 11 pi over 6. I'm making a mess right here. Okay. This is our dot for C. This is our cross for C. Okay. When we go from cross to dot, we said that is positive. And it's negative on the other side. Okay. So now we can start figuring out the flux. Flux in A with respect of the current in C. Okay. So the MMF withdraw with respect to C, but the integration we do it with respect of A. So first we need to figure out the angles that we are gonna have. So we are gonna start from pi over 2 here, pi over 2. That's where we have our dot in A, and we are gonna go to C, that where we have our dot in C. This is B. Okay. A second. Okay, let's, I think I have a mess right here, so I'm just gonna, here we have A dash, we have C, and we have C dash. Okay, perfect. Now we are going to integrate this way. We need to do it by parts, so we are going to go first to C dash. And so we're going to go from pi over 2 to 5 pi over 6. Okay, now from here to here we can see that the MMF is negative, so we have negative NIC over 2, and we divide by the reluctance, and we know that we're going to get mu naught times RL over G d5. And now we are going to go from C cross to A cross, so from 5 pi over 6 to A cross, that is here, over 3 pi over 2. And from here we can see that the MMS is positive, so this is positive too. So NIC over 2 times mu naught RL over G d5. Okay, so we know that our flux is going to be equals to, we can factor out our constants, mu naught RL over G. We are going to have minus pi over 2 minus 5 pi over 6 plus 5 pi over 6 minus 3 pi over 2. And this is going to give us that our flux in AC is equals to 1/3. It's going to be minus 1/3 pi NIC over 2 mu naught RL over G. And our self-inductance is going to be minus 1 over 3 n squared. Remember, the inductance is just flux linkage over I. So we're going to have n squared pi mu naught RL over 2G. Okay. So that's how we do it when we have two different yes, we are calculating mutual inductance. Now we're gonna see this example where we calculate the self-inductance. So we have a two-pole machine for the slots. Okay, so we are gonna name them. This is A, this is A dash, this is 2A, this is 2A dash. So this one here, that is pi over 2, is gonna be A, this is gonna be 2A, this is gonna be A dash, and this is gonna be 2A dash. Okay, we know that our MMF is Ni over 2 and Ni over 2. Okay, so again we follow the convention. When we go from dot to cross, it's negative, and it's positive the other way. And we're gonna do the same for 2A, so negative dot to cross and positive the other way around. Okay, so now we need to add up those two to get the total MMF. So we are gonna have Ni and Ni. We know that this is gonna be the maximum value because when these two sum up, for example, from 0 to A, they is gonna be the sum of Ni over 2, so we have Ni, and it's gonna be the same for negative. So from we are gonna have again here A dash to A dash. So we know that from 0 to A, we're gonna have Ni. Now, from A to A, we are gonna have 0 because here we have plus Ni over 2 and here we have minus Ni over 2. So for this length, it's gonna be negative. And now we have that they both are negative until from 2A to A dash. So from 2A to A dash, they both negative, so easily say 9. They both, one is positive and one is negative from A dash to A, so it's 0. And again, is positive the other way around. So around here we have 2 pi, I mean, and here we have 2 pi. Okay, so this is our MMF. So now they are asking us to calculate the self-inductance of the phase. So these two are the same phase, just in different slots. And so to calculate this, we are gonna have to calculate the self-inductance of A and the self-inductance of 2A. Okay, so let's begin with the first one. We know we have to calculate flux, so the flux in A with the respect of current A dash with its own current. So we are gonna go from the dot to the cross here. So from A to 2A is 0. The MMF is 0, so we're gonna get 0 current, so we don't have any flux here. So from 2A to A dash, we actually have MMF, it's negative MMF, so it's gonna be minus Ni, and it goes from 2 pi over 3 to minus pi over 2. Okay, well, and we multiply, but we divide by the reluctance, and we know that we are gonna get mu naught RL over G d5, and this is just NIA mu naught RL G times 2 pi over 3 minus 3 pi over 2. And this gives us a self flux, I guess, a flux in A of 5 over 6 pi in IA mu naught R over G. And if we apply the formula for the inductance, we are just gonna have that 5 over 6 pi times n squared, and we got rid of the I, so over G. Okay, now we have to do the same for the self-inductance of 2A and 2A dash. But if you see it here, it's gonna be the same, because if we go from dot to cross here, we have this negative MMF down here, and then we have 0. It's the same case that from A to A dash. So we know that those two are gonna be equal. So this is just equal to this, because if it's the geometry. So we know that the total of the self-inductance of the phase is just gonna be 2 times this. So it's gonna be 5/3 pi n squared mu naught L over G. Now, be very careful, because not always the geometry is the same for them. So you actually have to calculate it if they are not the same. The MMF is not the same. Uh, let's try to see another example. Here we have a two-pole machine, 6 slots, each one separated by 20 degrees, and we have six conductors and an uniform air gap. Okay, so first let's figure out the MMF, but it will help if we just draw a simple diagram of how the coils are separated. So we have here a pi over 2. So we have that at my pi over 2 minus 20 degrees, we're going to have the other coil. So that's just, okay, let me name it first. We're going to call it 3A, and we're going to get, we know that is this value. Now, a pi over 2 plus 20 degrees, we're going to have 2A, and that's going to be 11 over 18 pi. We have that at 3 pi over 2, we have our cross A dash at 3 pi over 2. We have our cross 2A dash at 29 over 18 pi. This is just 270 minus plus 20 degrees, and the same case here. 3A dash is 270 minus 20 degrees, so we have 25 pi over 18. Okay, so you do the calculations and turn the radius into radians. the radius, the degrees into radians. Okay, so we know that we have 6 conductors. So we know that we're gonna have an MMF of Ni over 2. So 6 conductors, this is gonna be 3I. So we know that we're gonna have 3I in some place here and minus 3I someplace over here. Now, when the three coils add up their MMF, we know that we're gonna have 9I. So here we're gonna have minus 9I. Okay. So let's start placing the angles here. So we know that we're gonna have 3A around here. This is the smaller angle. Then we're gonna have here A, and we're gonna have here 2A. Over here we're gonna have pi. Over here we're gonna have 2A dash. No. This is cross. And we are gonna have 3A dash, because it's the furthest one. Here we're gonna have a dash, and here we're gonna have 2a dash. Okay, that makes sense. And over here we're gonna have pi. Perfect. So we're gonna do the analogy like we did it before. Whenever we go from dot to cross, we have negative MMF. And the other, when we go from cross, let's say that all the other crosses are around here, to dot is going to be positive. So we know that for 3a, from 0 to 3a, this part is going to be positive for 3a. It's also going to be positive for a, and it's also going to be positive for 2a. So we know that from 0 to 3a, the MMF is going to be 9i. Now, from 3a to a, we know that it's going to be negative for 3a because it's going from dot to cross, so it's going to be negative for 3a, but it's going to be still be positive for these two. So we are going to have 3i in this space. Now here 3a and 3i, 3a and I, a 3i and I, a I'm sorry for my English, is uh, are going from dot to cross, so they are both gonna be negative, and only 2a is gonna be positive, so we are gonna have minus 3i. Okay, and now here also 2a is negative, so three of them are gonna be negative until we get to the cross of 3a dash, where this MMF is gonna be positive. Yes, so we're gonna go here until this MMF is gonna be positive, and only the other two are gonna be negative, so we're gonna have negative 3i here. And again, here this one becomes positive, and we have only one negative, so it becomes 3. And the cycle repeats itself here. We get 3i, and then we got minus I again. So this is the MMF distribution, and we're going to use it to figure out the magnitude of the fluxes. Okay, so let's go with the self-inductance in A. So for the self-inductance in A, we go from A dot to A cross. So we're gonna go first. We have to do it by parts because the MMF is different in each part, so we have to do it like that. So we go from A to A. So we know that A is pi over 2, 2A is 11 pi over 18, and we know that this MMF is minus 3i. Remember, flux is just MMF over reluctance. So we got 3i, and there, when we divide by the reluctance, we got mu naught RL d5. Okay, now we go to the next segment. So we have from 2a to 3a dash. This is minus 9i MMF. Now 2a is 11 pi over 18, and we have that 3a dash is 25 pi over 18, and we have, now we divide by the reluctance, and we know that we're gonna have this d5. Finally, the last piece is from 3a dash to a dash. So we know that 3a dash is 25 pi over 18, and a dash is 3 pi over 2. And we can see that the MMF here is minus 3I. And again, we follow the rest. That is part of the reluctance. And D5. Okay. Now we can collect the constants and do the integrals. They are pretty easy integrals because it's just D5. So when we do all the collecting, we're gonna get minus 3. I'm just gonna factor out 3. Mu naught at L over G. And this is multiplied by I. And we're gonna have the subtraction here, pi over 2 minus 11 pi over 18 plus 3, because factor out just the 3 here, minus 3 here, and it's 11 pi minus 18 over 18, I mean, minus 25 over 18 pi plus 25 pi over 18 minus 3 pi over 2. So it's just each one of this subtracted, and we add them up. So we have that a flux here is just gonna be minus 3 mu naught R G minus 23 pi over 9 times I, and this is gonna give us a, well, if we multiply the threes, okay, here we multiply the threes, okay, we are gonna have that this becomes positive, so we are gonna have 23 mu naught R I over 3G. Okay. So when we do this inductance, we multiply by N and divide by I. So we're gonna get 46 pi mu naught L over G. So this is one of our inductances. Now we have to do the same for the others. So we have to do A2 dash, A2 to 2 dash. We're gonna have something like this. Just gonna grab it from here. Make it smaller so it fits. And here we need this. Smaller a little. Okay. So we are gonna have something similar, but it's gonna change our, yes, from where we integrate, and also the magnitudes of the MMF are gonna change. Okay. Okay, for the first piece, we have we are going to integrate from 2a to 2a dash. So for the first piece, we have that is minus 9 in magnitude the MMF, So we are gonna here minus 9. And we are going from 2A to 3A dash. So we just plug those angles. 11 pi over 18, 25 over 18 pi, 25 pi over 18. And now here the MMF is minus 3. And we have, there we go from 25 pi over 18 to 3 pi over 2. And for the last piece, we go from A dash to 2A dash, and that is actually a positive MMF of 3. So we have here a positive MMF, and we go from 3 halves pi, 29 pi over 18. Okay? We do the same, we collect the terms. So I'm gonna factor out again D3, mu naught at L times I over G. And here we're gonna have minus 3, 11 over 18 pi, minus 25, 18 pi, minus 25, 18 pi, minus 3 pi over 2, plus 3 pi over 2, minus 29 over 18 pi. Okay, and this all is just gonna give us 3 mu naught L over G times 7/3 pi I. And when we calculate the self-inductance, we multiply by N and divide by I. So we're gonna have 42 pi mu naught RL over G. Now we have to do the same for the third coil, but if we look at it, if we try to do it for 3A to 3A dash, we see that we're gonna have positive 3, minus 3, and minus 9 again. So it's just gonna be the same that from 2A to 2A dash. So we know that this one, 2A to 2A dash, is the same that the self-inductance to 3A to 3A dash. It's similar to what we did to the last example. So the self-inductance of the phase A is just gonna be 46 pi mu naught RL over G. Thus, this is the first self-inductance we calculated, plus 2 times 42 pi mu naught RL over G. And this give us a total of 130 pi mu naught RL over G. Okay, hope this helps to understand how to figure out the MMF and the self-inductance and mutual inductance of a electrical machine.